回このNuCypherっていう、会社に、今回ワークショップやってもらうんですけど、まあ、彼らアメリカのベースの会社でして、で僕らもそのリトルモンスターっていう会社なんですけど、ベースはニューヨークでして、まあ、事業として何やってるかっていうと、インキュベーションっていうものをやっていて、まあ、インキュベーションって何かっていうと、教育と、まあ、投資っていうものを主にやってます。すみません、ちょっとビーノスみたいなスライドというか説明はいっぱいないんですけど、まあ、教育と投資をやっている会社ですと。で、まあ、最近ですと、茨城大学さんだったり、滋賀大学さんだったりっていうところと、そのブロックチェーンの講座っていうものをやらせていただいていて、で、そういう啓蒙教育活動っていうところの中で、今回こういうワークショップだったり、ワークショップみたいなものを、まあ、いくつかやらせていただいてます。で、最近ですと、まあ、ブロックチェーン僕ら特化している会社なんですけれども、それと付随して、まあ、STEM 教育っていうものに力を入れてまして、まあ、STEM っていうのは、サイエンス、テクノロジー、エンジニアリング、マスマティックっていうものの、頭文字を取って STEM 教育っていうんですけど、まあ、僕らもそのブロックチェーンに限らず、まあ、広く STEM 教育っていう文脈で捉えて、いろんな教育をやっていて、まあ、明日ですね、まさに明日27日、昼頃渋谷で、その STEM のスクールっていうものの体験授業をやらせていただきますので、よければご参加いただければと思います。まあ、リンクについてはちょっとまた後ほど共有させていただければと思います。じゃあ、そろそろ講師。あとそうですね、ブロックラビットっていうメディアもやっていまして、ここでいろんなブロックチェーンのその情報というかっていうものを、ここで、いろんな情報っていうんですかね、ブロックチェーンの情報っていうものをここでお届けさせていただいております。ここもリンクちょっと後で共有するので、軽く見ておいていただければと思います。はい。っていうところで、そろそろ講師の討論をお出ししようかなと思います。Hi, John. Can you hear me?
Hi. Yes, I can.
Yes. So sorry, we are just briefly explaining about the background of how this workshop has been ordered. So I guess it's time for you to present. So please take it away.
Sure. Thank you. All right. Let me share my.
I guess the volume is this. Oh.
All right. Let me get set up here so I can see everything. Okay. Hi. My name is John Pacific. I'm a cryptography engineer at NuCypher. Essentially what that means is I work on implementing some of the cryptography at NuCypher, which is stuff like proxy re-encryption, as well as doing some research in fully homomorphic encryption, which is also really fun. And I'll touch upon that, everything that we do in this talk, as well as go over an introduction to encryption and cryptography as well. So let's get into this. So what our agenda covers is we have an introduction to encryption, an introduction to public key cryptography, hash functions, very briefly, digital signatures, and other advanced cryptography, as well as what we work on at NuCypher, proxy re-encryption, as well. And I'll also be going through an entire code walkthrough of our code base so that you guys can fully understand exactly what we're building there. As well as we're also going to be discussing why we use Ethereum at NuCypher, and then a little bit of what fully homomorphic encryption is and why we're interested in using it. So to begin, we'll go ahead and do just our introduction to encryption. Starting off, we're going to talk about symmetric encryption, what that is. And then we're going to dive into what is called classic ciphers or classic cryptography, and as well as modern symmetric ciphers that people use today. So symmetric encryption is very simple to explain as a concept. We have a single document right here is like a Word document. And we derive a secret key here. And then this data, using an encryption function or an encryption algorithm, it gets encrypted and the data gets scrambled. And then to decrypt it, we use the same key. So it's the exact same secret key that you came up with in the beginning here to encrypt it. And it's used to decrypt it here. And then you get the original text back. So to make that very clear, what happens is we take the exact same key, usually a very random string, random bytes, and we use it to encrypt the data using an encryption function, and then it gets decrypted with the exact same key. There are problems with this, mostly that lie with what we call the key transport problem, which is how we transport the same key used to encrypt the data, and then how we transport that key for someone to decrypt that data with that very key. It's a complicated problem because getting that key safely from person A to person B is very hard. And so we've come up with other crypto systems for that, which I'll touch upon later, called public key cryptography, that helps answer this problem a little bit. And I'll really get to dive into how that works there. But next we're going to go well back into the past and history for the history of this kind of encryption. So we have classic ciphers, and this is something that most of us are probably familiar with already. We've kind of been playing with these since we were kids, and people in history have been using these for a very, very long time. For example, what I have pictured here is what is called a cipher disk. It's what's called a substitution cipher. This particular one was used by the Knights Templar early in the, I think, 16th century. So what this simply is that we have our alphabet here, just our standard English A to Z alphabet on a disk. And then we have the other letters here that we want to substitute. So if we want to encrypt the message, say something like the word say, your key would actually be what the offset of this is. So if this is an offset of 0, meaning that A is equal to this character and equal to this character, we would actually rotate this disk in this direction. Unfortunately, I couldn't find a graphic to actually really demonstrate this to you guys, but it should be easy to visualize. Essentially, you just shift the disk in the direction you want a number of offset digits away. And so, for example, if you shift it 3 characters away, that's an offset of 3, and that makes your key 3 as well. And so if we were to shift it to the right 3 characters, that'd be 1, 2, 3, X. So X would be here, and then this character would be substituted for X. And then that way you could encrypt and encipher messages like that. This is actually very vulnerable to what is a form of cryptanalysis called frequency analysis. And in the English alphabet, the most common letters of words are E, A, I, O, and things like that. And so if we have like a very long sentence, for example, you could take this here, just this phrase here, Introduction to Encryption, Classic Ciphers. If you were to distribute letters based on the frequency that ciphertext appears for each character, then you would actually be able to break this sentence and break the plain text and figure out what the message is. So this is not secure anymore, obviously. And to give you an idea of how large keys are now, you can consider this like the maximum key size to be 26. That's all we have for the English alphabet. There's 26 characters, so there's only 26 keys possible. So to give you an idea of how large keys are today, I've done a little bit of math here. So the average, like an average size for a modern cipher, like AES 256 here, is 2 to the 256. And that's a very large number. It's so large, it's kind of hard to grasp how big this number exactly is, because computationally, it seems rather small. It's only 32 bytes. And we can fit that in, in every computer today. Very tiny calculators can compute these numbers very easily. But to give you an idea, the number of atoms there are in the solar system is 10 to the 57. That fits, we can enumerate every single atom in the solar system in 24 bytes. And that's a number this big. The key size of a modern cipher like AES-256 is 2 to the 256, and it is far bigger than the number of atoms there are in the solar system. So when we say things like, would you need a computer that's larger than the size of the sun to compute, to brute force the key space, the key space is what we refer to as all the keys inside of here. So you could say the key space of AES-256 is 2 to the 256. The key space here to enumerate every single key and to encrypt every single message possible with every single key would require a computer larger than the size of the sun. And so we build security on principles that allow us to build and construct ciphers that make it computationally infeasible for people to break in reasonable amounts of time. So we can probably say, I couldn't come up with an estimate easily enough. They're out there though, that they're pretty easy to find. But I would say it's probably something like, to enumerate this entire thing, it would probably take a few quintillion years to actually enumerate every single key. And so that's why it will just never practically be done. If we're going to be practical about it, 2 to the 128, which is half this key space, is also computationally infeasible to compute now still. And I think it's smaller than this number still, but it's still infeasible for us to calculate every single number. So as I said, 2 to the 256, much bigger than 10 to 57. And that's what we build security off of, is just really large numbers like this. So we're going to dive into what modern encryption looks like now. We have two forms of ciphers that for symmetric cryptography nowadays called block ciphers and stream ciphers. The reason why somebody chooses to encrypt a large amount of data with a symmetric cipher rather than a public key cryptography or asymmetric cipher is because it is quicker and less computationally heavy. And so asymmetric cryptography is very good at one specific problem. Again, I'll get into that later. That is the key transport problem. And it's very simple to encrypt with. It's only one key, same to encrypt, same to decrypt. And it encrypts this data really, really quickly. So a block cipher essentially operates on data in blocks, like in chunks. And if you can see in my graphic here, we have a block cipher encryption here with a plain text. So the plain text is organized in chunked data. If, for example, your data is less than the required block size, it gets padded with extra information at the end that then gets removed during the decryption process. But it gets initialized as well with something called an IV, an initialization vector, which helps randomize the data. And it really kickstart the encryption process. So these are what you probably are familiar with today. AES, which is the Advanced Encryption Standard, which is pretty much what most applications use for encryption nowadays. There's two other ciphers I listed here, which were also finalists. People don't realize this, but AES is not the name of the actual crypto system. It's actually called Ringdale. It's named after the names of the cryptographers who built this. And there was a competition held to choose the best one. AES was the most efficient. So Ringdale was the most efficient cipher selected. It was the fastest, and it was one of the most secure. And so that won. But there were two other finalists, Twofish and Serpent, which were also block ciphers. So I'm going to jump ahead into the stream ciphers. There's a difference between stream ciphers and block ciphers. So like I said before, block ciphers organize data into chunked blocks. And then they do operations within them, which I'll actually get into in the slide after this. And stream ciphers are very flat and very streamlined. It kind of sounds like what it is what they sound like. They're easier to implement than block ciphers. There's things that we want to take into consideration when we build things like this, like constant timing. And block ciphers are historically very hard to get timing correct. What I mean by timing is that when we have an algorithm operate, based on the inputs, it cannot take any more time or less time if the input only matches certain criteria. It needs to take the exact amount of time for every single input ever. If there is any moment, so we call this a timing leak, if there's any moment where timing information leaks some data or leaks some information about the data that was inputted into the algorithm, then we can actually infer some secret information and sometimes result in losing confidentiality of that encrypted data itself. So this construction is based on a one-time pad. And what this simply means is, I'm sure you're all familiar with just the operation of XOR. If you're not, it's simply just taking like, if we take the bits, we choose either or. So if it's 1, 1, we get a 1. If it's 0, 1, we get a 0. Essentially what we're doing there is building a plain text. Say you have a 16-byte plain text, then you would also need a 16-byte key, a random key. And then you XOR that plain text over the key, and that gives you your ciphertext. Normally, one-time pads are actually the most secure crypto system to date. It is what we consider information theoretical secure. This was proven by a cryptographer probably in World War II by the name of Claude Shannon. He proved that a one-time pad is unbreakable if it follows some constraints, like the key is never chosen again, the key is the same size as the plain text, and it's never repeated ever. The moment any of those constraints fail, then it's actually feasible to break the crypto system. So these stream ciphers are built on top of this principle. Essentially, it allows us to compact a lot of entropy, meaning just, you can think of entropy as just randomness, into the pseudo-random key generator here. So the pseudo-random key generator, given a key, like I said, a 32-byte key and a initialization vector, kind of similar to what this is here, to just kind of kickstart everything. We can extend a key stream. So it's like an infinite size, infinitely long one-time pad that can be compacted into this key and initialization vector. So given these two inputs, we can replicate this entire key stream. And then that way we can encrypt as much data as we want. Historically, these ciphers, these stream ciphers are very fast and very efficient. And we're thinking that this is probably where the majority of modern encryption is going to go to. So I'm going to go ahead and jump to the next slide, which details some of these, the difference between a block cipher and a stream cipher. So this is what we're looking at, is the operations of AES, the Advanced Encryption Standard. Essentially, we've given it a plain text. We can generate a round key, which is like, you can think of like when we do AES, we actually do multiple rounds of the same algorithm over and over and over and over again. For I think 256-bit security, I think we do 24 rounds. I can't remember off the top of my head. But essentially, this is what the operation that the round does. Essentially, we have like a sub box. We call this an S box or a substitution box. It's actually a lot like what I demonstrated earlier in this ciphertext, in the cipher wheel here, except it's very large. Like I said, we're dealing with big numbers now. And so it substitutes bytes for some other bytes. It shifts rows around, meaning that if we have like columns like a matrix, then rows will be moved around. It'll mix columns up, so sideways, and then it adds this round key. So it's like an XOR operation here. And it does this as many times as the standard dictates. And like I said, I think it's 24 times or so. And then it does, for the last round, it does one little thing and then it outputs the ciphertext. And so that's essentially what AES is as it stands and how it kind of works as a block cipher. And for decryption, it's actually the exact inverse of this here. So if you read this chart going down this way, you can read this chart going up this way, okay? So given on input of a ciphertext and our key, we do the opposite of this round here backwards. We're just doing this backwards. And we do that 24 times. And on the last round, we just do the exact opposite of this here. And then on the output, we get our plain text. This has been one of the most successful encryption standards to date. There have been no weaknesses found in it, as far as no critical weaknesses found in it. It's being used to secure a lot of data as we know it now, being used in internet browsers every single day. And on the next one, I'm going to show you the kind of like the mirror image of this for the stream ciphers. So if AES is the example of our block cipher that we're choosing here, we're going to show you CHA-20 poly 1305. And I'll get into what this poly 1305 thing is, but just imagine this CHA-20 part here for now. So this is what a stream cipher diagram looks like. Unfortunately, I couldn't find anything more detailed than this to put in the graphic, but I think it'll do for now. So you can see this as everything just moving downwards and having a variety of operations being applied to it. This is actually what we call a ARX based cipher, which that means is add, rotate, XOR. So what you're seeing here is a addition operation, or I'm sorry, that's an XOR operation. And then we have a rotate, and then, no, I'm sorry, this is an addition operation, a rotate operation, and an XOR. So as you begin, we generate keys. So we generate different keys for each round. So just like AES, we have the ability to generate different keys for each additional round. And I forget how many rounds are in CHA-20. It might actually be 20. But what we do is we generate 20 different keys. And then as we progress down this graph, we're going to add the keys together, add our data together, rotate this data. So just like this is like a left shift operation, if you're familiar with that part of programming. If not, don't worry about it. And then an XOR. And then we just keep adding and mixing all this data in until we get to the very bottom. And that's our ciphertext. So I'm not going to keep going into depth. And this is probably the most technical for symmetric cryptography that we're going to get. And it gets very technical if I keep diving down. So I'm going to try to avoid that. And hopefully this confusing part of it is done. But yes, the stream cipher is much simpler to look at, much simpler to build, much easier to do securely. And then if that's one thing you take away from that, that's great. Is that stream ciphers are easy to implement securely. Block ciphers are more difficult. But to be fair, we actually don't know a ton about ciphers kind of constructed in this manner quite yet. We're still doing the security research, but we think that they're secure enough to be used, and that's probably the direction that cryptography is heading. So getting into this for now, the poly 1305 part, if you remember, we called it CHA-20 poly 1305. What this is, it was actually a form of what we call authenticated encryption. What that means is it solves a fundamental problem with symmetric cryptography. And that if we go back to our substitution cipher, all the way at the beginning here, if you were to give me a ciphertext, what's keeping me from cutting off a bit or a byte or like just a letter from that cipher and then replacing it with another letter and changing the actual message of the cipher itself. So when you decrypt it, it says something completely different, right? So we call these things chosen ciphertext attacks. We can change and modify the bits and the bytes in our modern ciphers and try to weaken the security of them. So going into it here, what authenticated encryption does, it prevents this kind of attack and allows the person decrypting the data to say, this is the exact data that was encrypted for me, and it has not been changed. This is built upon things like hash functions, which I'm going to get into as well as also a different ciphers. So poly 1305 is actually something like an authentication code. It's like something that lets you know that something was, that the ciphertext that you've been given is actually the correct ciphertext you want to decrypt. And that way you don't get a tampered message. You can actually prove that your message was not tampered with. So what it does is given our plain text and some additional data that gets added. We're not going to worry about this, but given some plain text and a key and a number used only once, that's what NOT stands for, is number used once, only once. And into some encryption function, on the output, we get a ciphertext and we get a tag. What this tag does, it's a very small amount of data, but it lets us prove that this ciphertext has not been modified or tampered with by anyone else, and that it requires the key to actually generate. So what it proves is, for example, if you don't know the key, you're not going to be able to modify the ciphertext, because if you do modify the ciphertext, then the tag will prove that the ciphertext has been modified. And if you know the key, well, then you can change the tag and change the ciphertext. But so the security is predicated upon an attacker not knowing this key, which they shouldn't anyway. Again, this is why that key transport is actually a very fundamental security problem. And I'm underscoring this key transport problem because when we get into the public key cryptography part, I'll explain how we actually solve that problem. And it's actually fairly fascinating. But to just summarize, if an attacker doesn't know the key, they cannot change the ciphertext. And if they do know the key, well, they can. And then that's how all the weakness is. So again, the security is upon not knowing the key. All right. So jumping in. Hi.
Can I ask the participant for the question?
Yeah, sure. Let me stop sharing my screen. I think I do. Stop there.
質問とかって皆さんございますか？どうですかね？大丈夫そうかな。ちょっと軽くじゃあ、まとめというか、僕が分かった範囲で説明というか翻訳みたいなことをさせていただければと思うんですけど、最初このイントロのところで、ジョンは、この暗号化の歴史というか変遷みたいなところを説明していて、スタンダードなものとして、シンメトリック暗号っていうものがあって、これってシークレットキーっていうものを当事者間で共有して、情報を暗号化したり、複合化したりっていう方法があります。ただその場合、シークレットキーっていうものを共有するのは難しいよねっていう話をしていたり、あとはこの暗号ですね、例えばA、B、C とかいろんな、アルファベットのスライドがあったと思うんですけど、それに付随する暗号みたいなものを用いて文章の暗号化みたいなところをやっていましたっていう暗号の説明だとかっていうものと、あと最近の、でも、いろんな暗号方式がある中で、最近挙げられている問題として、近年、やっぱりパソコンの性能が上がってきていて、その暗号化自体のすぐに暗号が解かれてしまうっていう問題があると。そういった中で新しい暗号化方式っていうんですかね、っていうものが求められていて、今回紹介してもらったのはそのストリームサイファーっていうサイファーっていうのがそもそも暗号っていうらしいんですけど、ストリーム暗号、ブロック暗号、あとはこの AES って言って、いろんな新しい暗号方式っていうものを説明をしてくれました。で、これからまた、違う暗号方式っていうものを順次、ジョンが紹介してくれると思うんですけども、また何か質問とかあったら、スラックだとか、もしくはこちらで質問を集められればと思います。Sorry, John, I was just briefly, summarizing what you're saying.
Oh, sure.
Yep, so, okay. Can you proceed your presentation?
Sure.
Yep, thank you.
All right. Continuing on. Let's see if I get my... No. All right. So public key cryptography, otherwise called asymmetric cryptography, and I'll explain why it's called asymmetric cryptography. But public key cryptography simply means that when Alice wants to encrypt a message for someone, she gets to use someone else's key. And so say if Alice wants to encrypt some data for Bob, Alice is going to use Bob's public key. And then Bob's going to decrypt it with his private key. Okay? So we can see these that when we say asymmetric cryptography, we mean that Bob when he tries to encrypt or decrypt a message, he uses one key for encryption and a different key for decryption. So you can see this diagram here. Alice is sending a message to Bob. She encrypts it with Bob's public key, and then Bob can decrypt it with a private key. So these two keys are different, but as this thing says, keys are different but mathematically linked. So we'll move on. There's two primary public key crypto systems that are in use today. These are elliptic curve cryptography and RSA. I'm going to spend most of my time on elliptic curve cryptography because that is what is pretty much the modern standard. It's what everybody should use. And RSA is old. As you can see, it's from 1977. And most people go with elliptic curve cryptography today. So that's what I'll spend my time on. For an elliptic curve cryptography, the private key is a large random number chosen at random. To be simple, this curve here has an equation. It's actually, we generate a very large, what we call a finite field. You can think of it as a massive clock, one that has 2 to the 256 numbers on this clock. And we pick a number off of it at random. The public key is a point on the curve. So when we generate this private key, we can derive from it a public key, which is like a point on this curve here using this equation, right? So we can actually derive a single point from this equation here. It is, like I said, it's the preferred asymmetric system today. The curve that Bitcoin uses, that Ethereum uses as well, is called SecP256K1. It has 2 to the 256 secret keys. So if we remember how large that number is, that's how many keys that you can actually use on this system. The keys are actually much shorter than RSAs, and the security of this system depends on the hardness of the discrete logarithm problem, and I'll dive into that in a bit. But just to touch on RSA, RSA is old. It depends on the hardness of prime factorization, which is like a very elementary algebra 101 sort of problem, where everybody remembers how hard it is to factor prime numbers, and you have to do certain things to do it right. And you can see that we use like it's pretty much like your secret key is going to be very large prime numbers. And there's problems with generating those prime numbers. And that's why everybody pretty much prefers elliptic curve cryptography today. And that's where you're going to see it more in the wild. So we'll move on. An implementation of this, and what I'm going to talk about now, is this key transport problem. If you remember how much I was saying and stressing how hard of a problem it is to actually solve, what I'm going to say here is given some sort of common information, in this case, we're going to use an example as paint. So what we're going to do is, say Alice wants to encrypt a message for Bob, but she doesn't want to transfer this key that was used to encrypt this data for Bob. She doesn't want to transport that key through the internet open, right? She has to encrypt it somewhere so Bob can decrypt it himself, and only himself, and decrypt his original data. So we're going to use colors here as an example. Given some common paint that everybody knows, some public paints, Alice and Bob both have yellow paint, and they can add in their secret colors, and they get unique colored paint. All right. So what we demonstrate here is, this is like, you can think of this color of paint as Bob's secret key. He's not going to share this with anyone at all, but he will share this paint color with the public. He's going to share this with anybody on the internet. Okay. So what they do, this is what we're going to describe as the Diffie-Hellman key exchange. This is a method of generating that key to encrypt that data that Alice wants to encrypt her data with, so that Bob can decrypt it, without ever actually revealing this key in an open channel. It allows them to derive secret information, a secret key, over a public channel. This helps secure that public channel and makes it a confidential channel. So Alice and Bob generate their secret keys, and they generate their public transport color. Alice gives hers to Bob. Bob gives his to Alice. And then they mix these colors with their own secret colors here. This is, again, they're mixing the key. This is the information that Alice gave Bob. This is the information that Bob gave Alice. So Alice mixes this information with her secret key and derives this common secret. And Bob can do the same. He mixes the color Alice gave him, adds his secret key to it, and comes with the same color that they both have. Now this common secret is what is used in that original encryption function I was talking about earlier, AES 256 or CHA-CHA 20. So what we're simply doing here is we're just using this to encrypt we're just using this to encrypt a key. That's all we're doing. We're not going to be doing anything else with it. We simply just use the public key system to encrypt a key so that Alice or so that Bob can then decrypt the key and then decrypt the data. It's a two-part process. So this is just a mathematical look on it to help maybe solidify it. We have two public parameters here. And I'm not going to bore you guys all with the math, but essentially Alice and Bob will just pick just a random number. And this is not at all like a real world example. These numbers are very small. Like I said, we deal with really large numbers now. But yet Bob and Alice will pick a random secret and they'll calculate a public key, right? So they'll calculate a public key, call it A. And so they take some of these public parameters and they use it to derive this, and then they can calculate the secret key. And so if you follow this along and you actually feel like doing this, you can pull out a calculator and you can actually calculate this and you'll see that these are the same thing. So and also like show you, to give you an idea of what the modern versus what the toy examples look like, an elliptic curve can be defined with this equation here that I've made here, right? So this is actually what an elliptic curve looks like if you graph it on a calculator or something. But to give you an idea, this little curve here is a toy. Like I said, we operate on really large numbers, what are called finite fields. Like I said, you can think of this as an exponentially large clock, a clock bigger than the sun, for example, with tons and tons of numbers on it. When we actually implement it in the real system, the curve ends up looking like this, which is really hard to understand. But essentially, all it is that this curve, if we look at this as like a distribution of numbers, each of these points on here is a different number from this curve. So it doesn't look like this in the real examples because this is dealing with a infinite, it just defines a curve over just some toy mathematical example. But when we start implementing this with really large numbers, the curve kind of falls apart and it just becomes this distributed uniform mess of numbers. This is where that security comes from, right? So what you're going to see here is even if you were to pick a number at random, it's uniformly distributed. It feels really secret, and it's not really going to be biased or anything, right? Because obviously, if we were to pick a curve here, some things are biased. Like you're never going to see something here, but you may see something only around in these parts, and that can actually leak secrets. But here, we can't leak any information here. There's no bias at all. This is a completely uniform distribution of numbers. If you were to pick something at random off here, it's hard to tell where's it from. So if you feel like researching this more, Peter Voll, a Bitcoin programmer, he actually generated what it may look like in a finite field, and that's what this is. So you can actually look this up on just Google it, and you'll see his answer to it and explain way more in depth of why this looks that way. Diving into elliptic curve cryptography a bit more and why it's so hard. what makes us suitable for cryptography, we have the discrete logarithmic problem. So essentially, we have types of cyclic groups. What a cyclic group is, you can think of it, like I said, as just a really large clock with a bunch of numbers on it. And what that means is, like, if you were to look at a clock right now, you'd see that it goes to 12, and then an hour later it's 1. So essentially, it has a modulus, which just means that it's like a ceiling. The number will never go higher than that, and it just goes all the way around, except on really large numbers. So elliptic curves are just a way of generating these really efficiently. So to avoid I don't want to go into the math a whole ton, but essentially it allows us to pick a random number and another element from that. And when you raise this number, just like an exponent, this gives alpha to the x is congruent to this other element that we got. It's really hard to derive the output of this equation. So alpha to the x is the output of alpha to the x. This number here just becomes very, very difficult to find x from. So given alpha and given this number, it's hard to find x. We believe this to be a very computationally hard problem called the discrete logarithm problem. That's what that's what elliptic curve cryptography is based upon today. So before I go in there, I'll ask if there are any questions about anything I've covered so far before we dive into cryptographic hash functions. So if anybody has any questions, feel free to ask. You're good?
質問とかって今ありますか？彼らの技術についてっていうよりかは、暗号技術、暗号方式の説明みたいなところを今やっていて、今は公開鍵暗号方式っていうところですね。これはビットコインに採用されている暗号方式で、いろんな、要するに暗号化っていうと、暗号化っていうと、暗号化されたデータにどっかで暗号で解かれないといけないんで、それをするためには秘密鍵っていうものをその相手に共有しないといけない。その鍵をどうやって共有するかっていうのが難しいっていうふうに、言われていて、でそういう中で最近、例えば暗号通貨だったりブロックチェーンっていうところで取り上げられているのは、この公開鍵暗号方式っていうところで、特に楕円曲線暗号っていうんですかね、っていうものが取り上げられていて、そこの説明を今、ジョーがしてくれていました。ちょっとそこら辺の詳細な説明は僕もできないので、Google だとかで調べていただけるといいと思います。Sorry, John, to interrupt your presentation.
Okay. All right. Shall I continue on sharing?
Yep.
All right. So, on to cryptographic hash functions. This is going to become much simpler now, much easier to listen to, less math. But essentially, what a cryptographic hash function is what we also call a one-way function, meaning it's not like encryption. It's like encryption that when you when you're given an input, it will scramble all this data. It will perform some mathematical operation and give a fixed size output. So for example, you can input 2 gigabytes of data and then get a 32-byte output that is unique to that 2 gigabytes of data. We have security requirements that we consider. So we have collision resistance, second preimage resistance, and preimage resistance. Essentially what it means is that given some input of this data set, it's going to be very difficult to find some data that given an output from this hash function, it's going to be difficult to find the input to that hash function. As well as given some output, it's going to be very unlikely that you find something that hashes to the same output that is different from the original input. So you can see here, it's difficult to derive M1 and M2 such that M1 is not equal to M2 and that the hashes of M1 is equal to the hashes of M2. So all you need to simply know is that for hash functions, when they're cryptographically secure, it's nearly impossible to derive the inputs from the output. And it's also impossible to find another input that is equal to the same output as another input. That's a little confusing, but it'll make more sense when we keep going. For some applied examples, there's two hash functions that are in use in these two common cryptocurrencies. So for Ethereum, we use Ketchak256. And then for Bitcoin, we use SHA-256. In fact, it's hashed twice. So we'll move on from here. Just to give you an idea, we have the input data Fox that goes through a hash function, and we get a digest. We get just this output data here. Then we have the red fox jumps over the blue dog. It goes through a hash function, gets a completely different output, and that they're nothing alike, even though they use the same word. And now we can even change a tiny bit of data. The red fox jumps OUER, the blue dog, and it's a completely different hash function that looks completely random and indifferentiable from this. So no matter how related the inputs are, the output will always be random. All right. So what this is going to lead us into is digital signatures and how we actually use these to work on data today. So digital signatures are implemented using those public key crypto systems. Essentially, they allow you to sign some data, just like a normal signature on a piece of paper that verifies that you've seen something or you've authorized something. This allows you to verify that this data, indeed, that this data came from you, that you've acknowledged it, or something like that. It just lets you to prove that this data was yours, or you have acknowledged this data with your private key. It's like identity almost, but not quite. So given an author of some data, they can sign this data and get a signature. That is then able to be verified by their public key. That way you can generate this data so that everybody can acknowledge, oh, this came from Alice. Alice encrypted some data. She signed it to prove that it came from her key. And then anybody can verify that it came from her public key. So an example of signing messages in Ethereum is like this. We have const message. We hash the data first. So that's why we dove into hashing beforehand. So simply, we have this output here. This is actually what someone is going to be signing with their data. It's just this digest, some of this data here. And then they can sign it and they get like the signature data, which is usually just like a combination of like two really big integers that they can perform through some function, which I'll get into later on this verification. So there's, just to give you some examples, Ethereum, Bitcoin, Litecoin, they use SEC-P256K1 for signatures. This is a curve, an elliptic curve. These both are elliptic curves. Particularly if you want to dive into this and really start learning more, the curve variant uses is a Weierstrass curve. The curve definition is here. It's very simple, very easy to define curve. This is why Bitcoin originally was chosen for this curve, or why this curve was chosen for Bitcoin. Another curve is ED25519, which is kind of a bleeding edge curve right now. We're seeing a lot of adoption. People like Dash, Stellar, Monero are using these kinds of things. I think Monero actually uses curve 25519, which is kind of related, but I'm not going to get into that. The curve variant is called a twisted Edwards curve. And this is what the equation looks like. It's a bit more complex, but we also believe it has certain properties that make it much more preferable, like performance and efficiency. So to give an example here, this is an example of a hashing or of a signature algorithm. We call this ECDSA. It stands for elliptic curve digital signature algorithm. So I'll just run through it very quickly. But essentially, we calculate the hash of this value M, where M is the data that someone's going to be signing with their private key. So we calculate this E, and we just start deriving more and more information from it. We pick a random number on this elliptic curve. We calculate a point from that curve. Then we calculate what we call this as a knots. And then we calculate the signature here. And the signature is this pair of two information, this R and this S value derived here. And given this information here, anyone can now verify that this data came from a specific public key. And this is fundamentally how kind of blockchains are starting to work, right? Now we're signing blocks of data and we're linking them together from one block to another. And this is now we have like a signed linked list, and then we can start adding in our proof of work and everything. And that's like where blockchain kind of grabs its power. And it all derives from the power of these digital signatures. And I really implore you, if you really want to learn more, you can dive into ECDSA and start just making your own signatures and going into it and figuring out how these things work. So we're going to briefly touch upon other advanced forms of cryptography before we start diving into the NuCypher stuff. Some examples are ZK snarks and ZK starks. Essentially what they're being used for, these are what we call zero knowledge proofs, which allow you to prove knowledge of something without revealing any information of what you're trying to prove. For example, in this case, we're proving that an input that you actually have the ability to send money from this address, like in Zcash, and that you have ownership over it, and that you have the ability to send it to somebody. And that's what you're doing here. That's how Zcash works. ZK snarks are being used in Ethereum as well to build more advanced protocols. And we'll probably see more and more adoption from them. ZK snarks are new, kind of a competitor to it. Whereas ZK snarks, they kind of require what we call an interactive setup, meaning that it requires or a trusted setup where it requires that we trust the people who computed this original data, that we have to trust they did it right, or else the security will fall. So Zcash has been criticized for this before, but so far it seems that they're doing okay. And ZK snarks are kind of an answer to that don't require this trusted setup. Next is ring signatures. This is what Monero uses. Essentially, you can have a bunch of different keys and different signatures to group together, and then where you are one of them, and where the attacker is trying to figure out who owns a specific key. And this group will be so large that it's kind of infeasible for them to find which key it's from. So they don't know who made the transaction. There's other forms of zero knowledge proofs too that are being used in Monero called bullet proofs. I haven't included these, but essentially allows them right now, in this case, before these proofs, Monero was simply saying, had this transaction data in the open, you knew how much was being sent, but you didn't know who it was from or who it was going to, okay? But now with bullet proofs, they're actually able to try to hide the information like how much they're sending. Another form of advanced cryptography is MPC. What this stands for is multi-party computation. Essentially, it allows a person like Alice to offload computation of some data to a network of computers. And each network of computers will perform some computation on each fragmented piece of this data. So she can take some data set, split it up in times, and then send the data to different parties. And then each party will do their own sort of calculation and computation on this data. And then finally, Alice can reassemble this data back and then gain an entire computation from it. Essentially, it requires a network coordinates, some computational distribution, sometimes via blockchain, sometimes through traditional computation means. And then this data gets relayed back and forth, eventually coming to a point where Alice can reassemble the entire computation and get this data. The idea is that essentially you have a number of nodes in this computation network that are not going to act maliciously, or sometimes in a secure fashion that we can prove that nobody acted maliciously. And then they can just perform computations for that. So we'll dive into NuCypher now, what proxy re-encryption is. Arj went over a bit with you, and I'll just cover it up again. Essentially, given some encryption, given some data that's been encrypted with one public key, so Alice's public key, we can derive a re-encryption key that encrypts data from Alice to Bob, and then we can distribute this re-encryption key to a proxy. The proxy performs a re-encryption operation, which then allows Bob to decrypt this data. So at no point in time was the data actually decrypted. The ciphertext was literally transformed from Alice to Bob. Okay, so this ciphertext was literally transformed without ever being decrypted from Alice to Bob, and Alice can grant as much access to this ciphertext to as many people as she wants. So in this case, we're saying we're granting access from Alice to Bob. We're generating a re-encryption key here from Alice to Charlie, and the proxy simply performs this re-encrypt function for each person to grant them access. This is really great for access control, which is primarily what NuCypher has been used for, so we can build applications in a secure, decentralized, private manner. So I'll dive into what Umbrel is. Umbrel is our proxy re-encryption algorithm. It has some properties. It's unidirectional, single hop, non-interactive. What these things mean is for unidirectional, it simply means that it can only be encrypted in one way. So if Alice re-encrypts some data using a re-encryption key, if Alice re-encrypts this data to Bob, Bob can't re-encrypt the data using the same re-encryption key back to Alice. So we want this to be unidirectional, such that so that everything is secure in one way. So Alice never has to worry about if Bob is going to gain access to her data. Single hop simply means that given this re-encryption key, we can't derive another re-encryption key from it. So given this re-encryption key from Alice to Charlie, we can't derive a re-encryption key from Alice to Bob. All right. So it just means that it only works in one way. It can only go from Alice to Bob, and that re-encryption key can no longer be used for anything else. All right. Non-interactive simply means that Alice doesn't need to work with Bob to generate this re-encryption key. If Alice wants to grant access to Bob, she should be able to do so without Bob being online and saying, hey, I'm open for this data. If Alice should just be able to give it to Bob as she wants. So it requires no interaction from Bob's side at all whatsoever to just get access to this data. We use the KEM, DEM approach to this. And what this means is essentially it touches back on that key transport security problem I was talking about before, where what this stands for is key encapsulation mechanism and data encapsulation mechanism. So the data encapsulation mechanism is what I was referring to earlier, like AES 256 or Cha-Cha 20. And the KEM is what we actually use to encrypt that key with so that Bob can decrypt this data. We use the Umbrel KEM for this. This is a form, we use asymmetric cryptography to accomplish this. If you want to dive into the specifics of this is called an elliptic curve integrated encryption system, which simply means that we have an encapsulation system which allows us to derive an encryption key, encrypt some data, and then encrypt that encryption key for the recipient. So it's all integrated in one thing, and it's like a nice finalized encryption product. The data encapsulation mechanism can be any AEAD, like Cha-Cha 20 Poly 1305. We want to use authenticated encryption for this. We also generate proofs of correctness so that when the proxy generates this re-encryption key, or when Alice generates this re-encryption key, she provides this to a proxy, and the proxy performs the re-encryption. So if we go back to this diagram here, we want Bob to be able to know that the re-encrypted data was actually re-encrypted correctly. Okay. So we want Bob to know that he hasn't just been given garbage ciphertext. He wants to know that it's actually been re-encrypted for him and that it's been done so correctly. And so we actually use zero knowledge proofs for this. They're very primitive. They're very simple. It's nothing complex like the ZK Starks I talked about earlier. And so the real magic with Umbrel is, in comparison to other proxy re-encryption algorithms, is that it is collusion resistant. What this means is that normally if we look at this diagram, Bob and Alice has to essentially trust that this proxy is not going to give Bob access to this data outside of the time that he has been allotted to gain access to this data. So what we do is, instead, we can split up this re-encryption key. So what we derived here, we can split that up and distribute it to a different number of nodes here. So in this case, we have 3 nodes, and we distribute each one of these to 3 nodes. And then what Bob has to do to gain access to this is go to 3 different nodes. She has to go to a certain number of these nodes to be able to perform that re-encryption. Once it's been done correctly, he has gained access to it. Using our verifications of correctness, we can prove that each proxy acted correctly and non-maliciously and fairly. We have a staking token, the new staking token, which incentivizes and enforces this behavior. So if they misbehave, they get slashed and they lose their tokens. But if they behave, they earn an inflation reward. And that's going to come into when I talk about how Ethereum ties in to this whole thing here. So now we're going to begin.
Whether participant has a question.
Oh, sure.
Yeah, sorry. どうですかね、今、ようやくそのいろいろな暗号方式の変遷的なところにみたいなところからなと思って、ニューサイファーの暗号方式、ニューサイファーが独自にどういう暗号方式みたいなのがついているかっていう説明にまで入ってきたんですけど、いかがですかね。ニューサイファー、僕の理解をブロキシを通して、ボブだとかシャーリー、ボブとかシャーリーに報告する際に、ブロキシを通す僕の理解だとニューサイファーの方式っていうのは、ブロキシを通して、でなおかつボブとかシャーリーに情報を通す際に、それぞれのプライベートみたいなものをはい。それぞれ、例えばボブに送る場合は、ボブに対してプライベートで発行して、シャーリーに対してデータをする際に、シャーリーに対して、プライベートを生成するというような方式を取っているようです。ちょっと詳細について僕も把握できなかったんですけど、細かく単語みたいなところを追って調べていただけるといい。これからジョンが、GitHub からのコードみたいなところを詳しく見せてくれると思うので、また質問あったら、お気軽に申してください。So, do you
Hello.
Hello. My question is on how does ciphers either concentration resources? I mean, how does it take time compared to other conventional methods?
Sorry, I'm having a hard time hearing. Is it possible we can type the question into Slack or chat?
So compared to like conventional encryption, so how much computation resource?
Sure. So in comparison to normal asymmetric cryptography and something like a digital signature, just like an ECDSA signature, it's roughly the same, maybe a little bit more. And just by a little bit more, I mean just a few milliseconds more. We're talking about just a few. If you want to understand this mathematically, it's actually really simple. We're taking just like Alice's private key and doing some operations that are very similar to just division and multiplication, given a few other points and a few other pieces of input data. So it's really only like, I think we can do one in less than a millisecond, or something like, I think, 3 milliseconds. So it's nothing intense at all. The most intense part, computationally intense part, is actually generating the re-encryption key and distributing it. So what you're going to be seeing there is more network latency than you are actual computational latency or computational performance. Does that answer the question?
今の質問は従来の暗号方式と比較して、どのぐらい計算、コンピューテーションのリソースが計算されたのかというのに対して、ジョンが回答してくださったのは、従来の、大暗号電子証明方式っていうんですかね、ちょっと英語でECDSA とほぼ、コンピューテーションのリソースは変わらない。ちょっと若干NuCypherの方が数ミリコンマぐらい、時間がかかるんじゃないかなということで、ほぼ同じっていうのがありました。あとは大丈夫そうですかね。また質問があったら、じゃあ、スラックの方が気軽にしてください。Sorry, can you proceed the presentation?
Sure.
Thank you.
All right, so I'm going to dive into, let me see. We're going to go into our GitHub now, and we're going to actually read some code that we at NuCypher have written. We're actually going to dive into the NuCypher code base itself, and I'll spend some time here doing this. So this is our repo here. You can go, if you want to follow along, you can go to github.com/NuCypher, and you'll be able to see everything I'm doing here. All right. So to begin, we have our white papers, if anybody's interested in reading them. We have the NuCypher white paper, how our token is used and how the staking, like the economics of staking here, as well as the cryptography paper. And this is mostly what I deal with here is this cryptography. So if you're interested in more of the proxy encryption, it seems like you guys might be, given the computational performance question. You can check out this paper and actually try and check it out for yourselves. We also have a reference implementation of it on GitHub as well, which I'll actually point you to at the end of the presentation. And if time permitting, I will dive into that code base as well. But a great starting spot to get familiar with the code base is our examples. So we can actually, I'll show the Finnegan's Wake demo. Last week, Arj showed you guys the heartbeat demo. I'm going to show you the Finnegan's Wake demo, which is essentially us using this proxy re-encryption and sharing this data from this book, Finnegan's Wake, which is just a very esoteric English text that is very unreadable. We like to make the joke that it's the question of whether or not it makes more sense after encryption is an open question. So what we're going to be doing here is essentially we can see how to actually generate or how to connect to a re-encryption node. So we can see how we, given some information like a seed node URI, which is essentially just an internet, just a URL, and we can connect to this node we call Ursula. So if you remember our proxy re-encryption diagram, the proxy is someone we refer to as Ursula, and the encryptor is Alice. She also shares data, and the person who receives this data is Bob. So you can see here we have our policy in date time. So we simply just generate some time date and some time delta. So we're essentially generating a policy that says you can have access to this data for 5 days. And then we set our M of N values, which is this proxy, this threshold part where Alice will distribute shares of this re-encryption key to people on the network. So this N is the total number of shares to distribute. And this M value 2 is the total number of re-encryptions required to gain access to this data. A label helps us identify the data that you're encrypting, and it adds some security to it so that if at any time your key were to be compromised, then they only gain access to some subset of your data, not everything else. It's like a form of weak forward secrecy if you're interested in learning more about that. So this is where we see where all these actors start participating in our network. So for example, Alice gets instantiated. She knows some nodes on our network. She wants to learn about more nodes on the network so she can distribute this key. She has a public key that she's going to generate for the policy so that people can encrypt data and then share that data. We have Bob, who's the person who's going to be granted access to this data. And as well as our learning loop, what this is, the learning loop simply is a method for learning about other nodes on the network so that you can share data with them. You can think of it as like a replacement for a DHT. We actually replaced our DHT with this, so it's just a peer-to-peer learning method. It essentially goes to one node and says, who do you know? And that returns that information, and they go to the next node, who do you know? And it just keeps generating information like that. So we have this function, alice.grant. So that takes some information, Bob, a label, this IMVIN value I told you about, and the expiration. So like when Bob should not have access to this data. So what we're doing here is Alice is granting access to Bob here, and we get a policy out of that. And we're essentially saying that this policy is going to be valid for 5 days, and Bob is going to be able to decrypt this data within as many times as he wants within this 5-day period. So what Alice will do now, she'll save this public key and for Bob to find later. And what we're simply demonstrating here is that Alice doesn't actually need to be online anymore once this policy has been done. She can disappear from the internet forever, and Bob will still gain access to it as long as the policy is valid within time. So Bob is going to join the policy, is simply saying he wants to decrypt this data, right? He'll put in the label that Alice made, as well as her public key to identify it. And what we're doing here is declaring this character Enrico. We call him Enrico because he's an encryptor. He encrypts data. So Enrico is a completely separate person from Alice. And what Enrico is doing is just encrypting data with Alice's public key. We call this the policy public key. And then he's just encrypting this data here and just signing the data. Right? And then we can delete Enrico, so Enrico can actually disappear from the network. So all he did was he encrypted some data using Alice's public key and disappeared from the network forever. So Bob can then go and start decrypting all this data. So he finds Alice's public key, generates an Umbro public key, and we can actually just call this function bob.retrieve. He passes in some of the ciphertext, the source by data, and then a verifying key to prove that it was from Alice. And then this data gets decrypted. So if you did the tasks that Arj asked you to, you would have played with this a bit more, and it becomes much more clear when you start playing with it. Which I implore all of you to do is to play with it. It's actually it's very cool. I'm sure many of you will immediately see the use cases for it once you actually start playing with it. So to get more familiar with the NuCypher code base, we're just going to start diving into where these functions are defined. So we're going to exit out of the demo here and go back to our repository. So we're going to go to characters, NuCypher characters, and this is where they're implemented. And we have two files here, lawful and unlawful. We like to model malicious actors on the network to ensure that we're actually providing some guarantees of security. So we build people who may not function the right way. You can import a character that is not going to perform the way they should actually behave. So you can import, for example, an Ursula who's not going to perform her re-encryption duties, or she's not going to provide real data for Bob. And then we have our lawful characters, which just do the things that they're told. And this is like exactly what what you want to use and what we're going to learn about. So diving in here, we have our characters defined Alice. So this is the person who grants access to data. And you can see all the functions she has. She can generate K-frags, which is this method that actually allows her to share data and generate this re-encryption key. She also has this function called, or this method called create policy, which allows her to create this policy to share data with Bob. So we have function or methods that implement each other so that it's much easier for developers to use it. So create policy will allow her to create a policy and share this data and generate K-frags and distribute them to our network, right? And we have grant, which actually grants the data to the network and actually grants the re-encryption keys so that Ursula's or our proxy nodes can perform the re-encryption for Bob. Given a label, like some information from a label, we can derive a policy public key for it, for Alice's data specifically. And we also have a function called, or a method called revoke. And essentially what revoke does, it just simply goes to each node on the network and has them delete the K-frag. That way they can't grant access to any future, to any person, again, with that policy K-frag from Alice to Bob. So if Alice grants some data to Bob and Alice then calls this revoke function after some amount of time, Bob will no longer be able to gain access to it, all right? We also have defined our character Bob, who is the person who's being granted access to. This is like what your client would be to gain access to this data. Peek at treasure map. What a treasure map is, it's kind of what it sounds like. Alice generates this treasure map that tells you which nodes have the fragments that Bob needs to go to get the re-encryption performed. So peek at treasure map will just return the nodes that you need to know so that you can actually perform this re-encryption. Follow treasure map actually follows the treasure map, so that way you actually perform the re-encryption here. And it actually just, it goes to each node and will perform a function with them. And get treasure map returns the actual treasure map, the actual object itself. We have a variety of methods for these things to help you validate and perform operations for the network. Make compass for Alice will help you figure out, we'll verify that something is from Alice. We have construct policy A-track, which is this is all used internally. So if it's kind of bothering you what these are, you can start following the higher up functions like bob dot, or is it join policy, bob dot join policy, bob dot retrieve. And you can follow down how these things work here and kind of get a feel for what the rest of the code base is doing there. So just to clarify here as well, what an A-track is what we call a hashed resource authentication code, which allows you to say, this is the thing that I want to decrypt. So if we go to a node on the network, on the NuCypher network, we need to provide a way to say, hey, this is the data that I want. I want you to use this re-encryption key, and I want you to decrypt, or I want you to re-encrypt this data to me. So the A-track is what identifies that policy data for Bob. So for each thing here, we have just other stuff here as well, like get treasure map from known Ursula, which allows her to ask for the treasure map, who has this thing, and it allows you to return just this treasure map so that Bob can actually follow it again. Get re-encrypted cfrags. This is kind of an important one. Essentially allows you to retrieve these re-encrypted data. So you'll actually then get this re-encryptions performed for each operation, for each node in the network, and actually get the cfrags back. And bob.retrieve is just like I said earlier, it's the function that Bob will actually use to to actually get information from the network. So if Alice grants access to Bob, Bob's going to call bob.retrieve and decrypt this data. So Ursula is the other part of our code base. Ursula, she has these characteristics. She's a teacher, a character, a miner. So she mines the NuCypher token. She's actually generating inflation. She's getting inflation rewards for staking. She's also a teacher on the network, meaning that other people can connect to her and say, who do you know? So I can populate my list of nodes that are also on this network. Since it's a peer-to-peer network, they need to know who knows who. So Ursula is the person that is actually staking this data and performing the re-encryption. She is our proxy. She's instantiated with a variety of methods as well. So we have some like blockchain components, identity evidence, which proves that she is the person, she is on the blockchain. Her checksum public address, which is like her Ethereum address, as well as a variety of other things here. It's quite a big, this is a big character, so it's quite a complex object. But to be quick and short with this, since as implementers, you're probably not going to be mostly worried about the proxies. You're more worried about just Alice and Bob and those characters that actually let you use the network. So I'll be quick. We have REST information, which allows you to like have an API for development, so that when you stake her, how you talk to her. So we can instantiate also these Ursulas from a variety of methods. We can, from seed node metadata, from a REST URL. So like from just a URL on the internet, we can instantiate one from. We can instantiate one from seed node metadata. It's just like kind of like a deserialization method that we would know from like in demos. From a teacher URI, which is like another form of a URL as well. From seed and stake info is normally what we use for demos. You can see that if you go to the Finnegan's Wake demo or the Heartbeat demo that Arch demoed last week, you'll see us use this and how it's used there. She can also be serialized into just bytes, and this is just that deserialization method here as well. And most of this code is very readable. You can just literally just pick anywhere in the code base and just start following the function calls and the method calls down through it, and you'll start learning very quickly how NuCypher works. So that's a brief touch up on our actual characters there. Another great place to look at is our network. So you'll see here that we have our protocols. Pull this up. Just different ways of how we store stuff on the network, how we identify things on the network. We have an interface info, which is just kind of like just what you think it is. It's like an IP address and a port. Node URI, how we identify a specific node in the network. The middleware is also important as well. Essentially, how you're going to connect and contact the network, and how we underlyingly contact other Ursulas and perform other operations. So this is where you'll see stuff like enact policy, where we actually can deliver a kfrag to an Ursula, a re-encrypt operation, which performs this re-encryption. A revoke arrangement, we call an arrangement what we give when you give a fragment of this re-encryption key to an Ursula. That's an arrangement. And so revoke arrangement simply says that Ursula is to delete that kfrag. Node information to get more information from this node itself. Get nodes via REST, which is just tell us the nodes you know. So that's an important operation for network utility. That's where you'll also see stuff like here in our server protocol, our server module rather, where we can actually define like a REST server and a RESTful application, and actually each route where it's defined. So if you want to dig in there, you can see that there as well. I'm not going to dive into that. but as well as our policy stuff is really important, because if you really want to understand what we're talking about when we say arrangement or revocation, you'll see that here. So like an arrangement, a policy must be implemented by arrangements within Ursulas. This class tracks the status of that implementation. So that's like the number of K. This is a K frag that is given to an Ursula. We call a K frag a re-encryption key fragment that's been granted to a different Ursula. The policy itself, which is like this actual piece of information that says that Alice has given the ability to Bob, has given Bob the ability to decrypt some data and have it re-encrypted for himself. And this kind of defines a lot of information. You'll see A track and see exactly how it's derived. You'll see publish treasure map, a way to publish that on the network. Enact, a way to assign K-frags to specific nodes on the network. Federated policy. We have 2 networks at the moment. Our testnet is what we consider a federated network, meaning that we're not using the blockchain components just yet. There is no staking being done. We've simply just have a peer-to-peer network that active right now that allows us to perform tests on it and everything. So the federated policy would be a policy that is not granted over the blockchain. Rather, it's just granted from peer-to-peer. A treasure map, which defines where to go to get these re-encryptions done. And work orders, which are like this way to actually say, hey, I want this re-encryption performed and I want this data back. So the revocation as well as here is something I wrote. Essentially, it is a object that lets you send to a specific Ursula or a proxy node in our network and say, please delete your K frag or the fragment that we've assigned you, and it will get deleted. So continuing further, our CLI, this is actually quite an intense document, so I'm not going to dive into it a whole ton. But we actually have a command line utility built right now to help us perform staking operations, encryption operations, run nodes, etc. And so we've defined a bunch of functions here. If you're familiar with Python's click module, then you'll see how this is used, and it's really straightforward. It's just very long and lots of if logic, conditional logic to go into. But yeah. So that's pretty much it for an overview of the NuCypher code base itself. That should give you an idea. The blockchain part of it is the last part I'm going to go into, and I'm not going to go too heavily into it because a lot of it is just Solidity code. But this is like where we store our Solidity smart contracts that allow us to do certain things. So for example, like this is our token. This is the actual NuCypher token itself. It's not deployed yet. It will be soon, hopefully. And we will see, essentially this is what people will be staking. You'll see here as well as like some proxy contracts, which allow us to perform upgrades to our network. So we can have we can mark a certain contract as upgradable, and it allows them to actually upgrade this contract and perform a network upgrade. Policy manager, it just holds policy data, locks fees that we use for the network itself, and it defines everything like that we would use for the network. There's 3 main predominant use cases for the NuCypher network. They're briefly slashing or staking, node location, node identification, and slashing. So staking essentially says, when I put up the NuCypher token, I'm going to start receiving re-encryption requests. And so you'll start receiving fragments, and you'll perform re-encryptions, and you'll get rewarded for those re-encryptions. Node identification is how we actually select nodes on the network. So we pick things by essentially, we pick nodes by stake. So since we're a proof of stake system, essentially we're choosing the highest stake nodes at random. And when we do that, you're essentially sending a re-encryption fragment to that node, and then they'll perform those re-encryptions for you. So the blockchain really assists us in picking which nodes to do that. And then using this allows us to have a game theoretical incentive, economic incentive, so that we can actually enforce some collusion resistance properties for proxy re-encryption. This is what actually makes it secure. And then the slashing part of it, which is what lets us actually say, if you misbehave on the network, you'll get slashed and lose your token. So if you perform a re-encryption maliciously, meaning that you just provide garbage data instead of actually doing the re-encryption, you'll get slashed and you'll lose your stake. So it's pretty simple for the blockchain stuff there. The most of the complexity, I think, lies in the NuCypher code base itself and the networking and affiliated things like that. So let's move on to PyUmbrel. PyUmbrel is our reference implementation of proxy re-encryption of our Umbrel algorithm. And I'm not going to spend a whole ton of time here. This is what I would definitely suggest. If you don't have time playing with NuCypher, at least play with the PyUmbrel code base so that it lets you actually feel what proxy re-encryption, or get a feel for proxy re-encryption and how it works. This is our actual library. This has gone through security audits as well. It was audited by NCC and Trail of Bits. It's secure as far as we know. If you have bugs, please send them to us. Also licensed under GPL v3. But essentially, it's just a whole encryption library. It allows you to generate keys, signing keys, and then generate Umbrel keys. You can encrypt data, and then you can re-encrypt data. So we can do this by generating those re-encryption fragments. So this is the K frags I was talking about. And then you can set correctness keys for verifying the proofs that the re-encryption was done correctly. You can re-encrypt the data through these methods here. And then Bob can also decrypt it. It's on pip. So if you want to play with it, just do pip3, install Umbrel, and you'll get it. If you're interested in seeing the actual paper on this, then feel free to read this document here. It'll explain everything you need. Of course, if you find issues, please submit them on our issue tracker. Source code's also here as well. So I have some time left. I'll go ahead and dive into some of this. This is where maybe you'll start getting a feel for elliptic curve cryptography and how it's been implemented. So we call a curve being it's a big number on a curve. Big number, just a really big number that is an order of that's modulo the order of the curve. So we have some methods here. We can generate random ones, get the bytes, get the length of given the curve, get the length back from it. We can generate them from Python integers. We can generate them from bytes, serialize them 2 bytes, compare them, and we can perform all of our mathematical operations on here. So we have operations like exponentiation, multiplication, division, addition, subtraction, inversion, negation, and then just a modulo. Let's see, we'll go to the point here. This is where our points are actually implemented. So essentially what we're doing is wrapping OpenSSL here. So if you're familiar with OpenSSL at all, this will feel like a familiar but much more simplified API. So we can generate a random one, generate a point from affine coordinates, and serialize them to affine coordinates where they're both integers. Deserialize them from bytes, serialize them to bytes. You also get a generator from a specific curve. The generator is a point on the curve that lets you perform operations with the curve as well. And we also implement a variety of math operations as well: multiplication, addition, subtraction, negation. And so this is a full-blown elliptic curve math library that's ready. We needed this so that we can build Umbrel in a very secure production-ready environment. Normally, people would use like Sage, if you're familiar with other cryptography implementations. But we didn't really want to do that, so we just used OpenSSL. And we used Cryptography.io, which has a backend to OpenSSL. And that's how we did that. So if you want to see the actual proxy re-encryption itself and how it's implemented, you can go to this PRE module here. And you'll see it. Like Capsule is just, you can think of it as an encrypted key, encapsulated. We have a variety of methods on there for serialization. To set correctness keys, so this like allows us to generate proofs for it, to prove that it was encrypted correctly and it's from the right ciphertext. Generate K-frags allows us to actually create these re-encryption fragments. And so it's very easy to follow along in the math here and actually watch and see how it was actually implemented. So yeah, you can really dig in here and see how everything works, how the math works. And it's made to be very followable from the paper. So if you have the paper in one hand and the code in the other, it's very easy to put 2 and 2 together and figure out what's going on. Re-encrypt is the actual re-encryption operation. Somebody asked earlier what the computation was like. Well, it's literally here. I'll point it out here. It's only 2 multiplications. So it's very similar to just a signature verification. It's very fast and efficient. It's not slow at all. As you can see, this is the generation for this re-encryption. It's not slow at all. It's just a variety of math operations, just multiplications, divisions as well. We have encapsulate, which pretty much generates a random key and allows you to perform a symmetric encryption using that key. Decapsulate original, decrypts an encrypted key. This decrypts a re-encrypted key. This will allow you to encrypt data. Open a capsule, which simply allows you to just like break out the key after it's been re-encrypted and use it. Decrypts as well, higher level methods for you to work on. And this will be the last one I dive into for PyUmbral itself. But we have keys here. What keys do, it lets us just have like Umbral keys that make it easier for us to work with and implement stuff. We have a class for script, which is like a password derivation, password key derivation. So given a key, just a password, we can derive an encryption key from it, or some form of, just something that we can use to compare for time, using time entropy. So obviously, like human entered passwords are not secure. Usually, they're usually really bad. We want to replace their usual badness and non-randomness with something that is random. And that's what we use script for. It just lets us derive entropy, randomness from time, and hardness of computation. So we use that there. We can generate wrapping keys, unwrap the keys so that we can, encrypt and decrypt keys themselves. We also have the implementations for our Umbral keys as well. So we can generate a key, serialize keys, as well as get pub keys, and actually just return them to cryptography.io, public, private keys, like they are actual, they're like the actual cryptography.io Python module keys that we can do there. We also implement the public key stuff there as well. And then keying material allows us to deterministically derive private keys based on those labels I was showing earlier in the NuCypher code base. So that's pretty much it for this specific code walkthrough. I'm happy to go over anything else if anybody has any questions. If they want to see something more in detail, I'd be happy to show you. So I'll give a pause there. Are there any questions?
Yep. どうですか、皆さん、今の時点でだいぶ詳しく GitHub なぞりながら、そのNuCypherの技術っていうか、コードみたいなのを説明してくれたと思うんですけど。 Maybe one question from me. So you mentioned that even if Alice came offline, Bob can still retrieve the data. But what's the point of those features?
I'm sorry. Can you repeat the last bit again? You echoed a bit.
So even Alice can become offline, Bob can still retrieve the data, right?
So sorry, I'm still having a hard time understanding. You're saying when Alice encrypts the data, Bob can still gain access to it?
I mean, even Alice get offline, Bob can still access to the data.
I'm sorry, I'm having a hard time hearing there's an echo in my headset. I'm having a hard time hearing.
So you mentioned that even Alice get offline.
Yes?
Bob can still retrieve the data.
Oh, yes.
Yeah, so what's the point of the feature of the function?
So the whole point of the proxy encryption is that it's scalable. So Alice can encrypt some data for Bob, and Bob can gain access to it. We can actually do this in more scalably. So Alice can grant access to many different people. We use I'll go over some use cases again, but for stuff that's like healthcare data where you may need to grant access to multiple people and have access to that data at different times, it allows Alice to share that data.
今、僕がした質問っていうのは、アリスが、誰かにデータを共有したいって言ったときに、アリス自身がオフラインになったとしても、そのデータを共有できるっていうような機能があるっていうことをNuCypherではやっているらしくて、そのポイントがどうしてそういうふうにしたのかなっていうふうな感じの疑問を聞いたところ、より、スケーラブルにデータの共有みたいなところをやろうとした際に、アリスが常にオフラインにいるよりかは、オフラインのデータの共有ができた方が、より多くの人に共有出すことができるんじゃないかというようなことを言っていました。はい。で、以上でジョーからの説明は終わりになると思うんですけども、何か質問を皆さんの方からございますでしょうか。大丈夫そうですかね。So yeah, I guess we are quite good from our side.
Okay. Okay, I'll go back to the presentation and continue on.
Oh, you said that.
All right, so I'm going to go into something that is very experimental for NuCypher, something we are working on right now. It's called fully homomorphic encryption. So essentially what fully homomorphic encryption is, it allows us to encrypt some data and then perform some computation on that data, on the ciphertext of that data. And then decrypt that data, and it would be the same as if the computation was done on the plain text. So with this graph simply showing, what this image is simply showing is that we have some data, we can apply a function to it, and we'll have the function applied over this data, right? So you could say we have some number, say 3, and then we can add another number to it, say 3 as well. And on the output, we should have 6. What a fully homomorphic encryption allows us to do is encrypt this data. So we encrypt 3, we can add, we can perform an operation on the encrypted data, and then on the output, it will be the exact same as if you had encrypted the operation in the plain text of it. So essentially, you can encrypt, say, the number 3, encrypt another number, like say 3 again, and add the two ciphertexts together, and you'll get the encrypted output of 6. And to actually reveal what is inside of that, what the actual output is, you have to decrypt it and see it. NuCypher has been working on this in research. It's something I've taken a special interest in. At ETH Berlin in 2018, we won the hackathon. I built this thing called Sputnik, which was essentially the very first homomorphic smart contract, which is essentially just a method of implementing homomorphic encryption on smart contracts so that we can perform private computations and achieve some sort of input confidentiality for smart contracts now. On Ethereum, smart contracts aren't private, they're in the open. You can see the functions that they perform, which is fine, but the input data is not private. So everybody can see what the input data is to the smart contract. And fully homomorphic encryption is used to prevent, is to keep the confidentiality of that information. Some use case for fully homomorphic encryption I demonstrate here is like patients can send their encrypted medical records to some computational party, and the nodes will run computation over the ciphertext itself without gaining access to the plain text. And then on the output, scientists, researchers, doctors, whoever can gain insights from that computation. Very recently and more modernly, we've seen people use FHE to perform like private machine learning and build neural networks with it, and which allow them to do like training data or to train AI models on encrypted data sets. So we're extremely excited about it. It's just something we've been working really hard on. And it's kind of like our long-term goal is to be able to build some semblance of fully homomorphic smart contracts. To get more information on NuCypher, you can go to our website, NuCypher.com. You can see everything I showed you guys at the NuCypher on GitHub. We have our GitHub there. You can see all of our repos there. PyUmbral is also on GitHub. What I also showed you, our homomorphic encryption library is open source. You can go to github.com/NuCypher/NuFHE to find it. If you have any questions about development, about how to use the network, you can join our Discord and we'll answer them as soon as possible. So we do all our development in the open, so you're very welcome to see it. If you want to see our white paper and exactly how the NuCypher network operates from a high level, you can read our white paper and that'll explain everything. You can also feel free to email me at john@nucypher.com. I'll answer every email you send, as well as sending just a message at hello@nucypher.com. We'll be sure to get back to you. For some early adopters, some examples of who's using us, we have people like MediBlock, MedCreds, MediChain, Point Nurse, who are using us for medical data sharing to keep that data secure and actually sort of give back some role of data ownership to patients and to let them have selective privacy in who they share their medical data with because it's very personal. Automobile data, car block. So for example, we were just participating in the Mobi hackathon where we used the diagnostic sensors in the car to encrypt data and share it with insurance companies and as well as other people as well. And so that car owners can have selective privacy with who they share that data to. People are using us Datum for location data to share that data, as well as Dr. Chain for genomics data. We have for protocols, Internet of Things from Spirity and Chain, as well as also other medical data protocols. We're being used for access control in decentralized databases, Bluzell, Fluence, and Volt, as well as user data monetization at Swipe and Datum as well, and sharing economy with Origin. So people can share data from one another securely. And so essentially what NuCypher, if I can overview what the biggest power of NuCypher is, it is the ability to have selective privacy and selective access control to who you grant your data to. So we can empower users to own their data and only grant access to it as needed, so that people never have more data than they need to prevent, another big Facebook or another Google or another Amazon from owning all this data and the monopolization of this data. So it's in the hands of you yourself, and you can give data back or grant access to the data as needed. So that concludes this presentation. I'll answer any questions now as well.
Yeah, there's one question.
Great. So hello.
Hi.
Hi. So my question is about fully homomorphic encryption.
Sure.
Yeah. So I'm just guessing on just for example, how long it will will it the data after the encryption by fully homomorphic encryption? Just like example, I'm just guessing that it will be a very large uh, byte or very large data, even if we just encrypt just small letters. I'm just guessing. So it will be very large data by after fully homomorphic encryption.
I'm having a hard time hearing questions, but to reiterate, I think what I heard was how are we handling very large ciphertext? Like you're saying that when we encrypt the data, it gets very big. Yeah, great. So that's actually not, it's still a huge problem. Yes, these ciphertexts are very large, but when we compare them to other traditional solutions like multi-party computation, what we're actually doing there is sharing very large data as well. So MPC is also used to perform computation, just like FHE is, except it's a bit more complex and some problems are more hard than others than they would be in FHE. But for MPC, we're having problems like network latency. We're having problems like sharing huge, it can be even smaller ciphertext granted, but at the same time, we're sharing gigabytes of data over network back and forth in like almost like a star layout, right? Like a star diagram. So you're sharing data like almost exponentially times on the network. And that's problematic for many ways. But if I'm going to start speaking more theoretically and in a research perspective, is because what I do, I'm hearing an echo. Okay, it's gone. But what I do at NuCypher also is some of this research, and fully homomorphic encryption is at a point where it is becoming much more promising and efficient. Ciphertexts are large, but they are getting smaller. We're finding ways to compress them and more efficient ways to store the ciphertext. So for example, we have something called ciphertext compression with fully homomorphic encryption, which essentially is, you can think of it as like encrypting the data with a normal, like symmetric cipher like AES. And this has been done already. We can encrypt the data like with AES. And so you'll have like only a few more bytes than your ciphertext. So say if you have a gigabyte of data, or I'll make it smaller. Say you have 100 megabytes of data, you're still going to have 100 megabytes of data after this encryption. And then it's done in an efficient manner so that homomorphically it can be encrypted and evaluated. So then you transfer this encrypted ciphertext into the homomorphic domain. So you pass it along to the computer who's going to perform the homomorphic operation. And they actually perform the decryption on this homomorphic, on this data. And that way it expands, the ciphertext gets large in memory, but in storage, it stays small. And also in transit, we can keep it small. And there are last mile problems to this, and that's something that I'm currently looking for answers to. But they're essentially, just to give to briefly answer the question, yes, large ciphertexts are a problem. There are other problems. I don't think performance is a problem anymore personally. We've accelerated FHE to be exceptionally quick. So I'm not at all afraid for performance, but for ciphertext that does concern me, but not as much as I think you feel it does. There are methods of keeping the ciphertext smaller, and we will see things get much smaller as time and research moves on. What things do concern me are proofs, actually, zero knowledge proofs, to prove that encrypted data, homomorphically encrypted data, is what it is. And for this, we actually need some advances in lattice-based cryptography, and that's where NuCypher is actually taking a little bit more of a turn, is actually looking more into right now, is lattice-based cryptography and generating and building systems that allow us to provably do this. So we can do this in a distributed manner. I hope that answers your question.
今の質問っていうのは、順動暗号方式っていうものを用い、膨大な量のデータをその暗号化した場合の懸念点、膨大なデータを扱うかっていう問題。だから暗号化です。ちっちゃいデータでもその暗号方式がどこ
健吾くん、これミュート解除するのどうしたらいいよ。
Sorry, John. The mic was badly. Mic was going.
Yeah, it's quite all right.
Yeah, let me just translate the question and your answer. その今いただいた質問っていうのが、元のデータの順動暗号方式っていうものを用いると、その元のちっちゃいデータを暗号化した後の暗号化できるっていうものが、大きくなってしまうっていう懸念がある中で、その正確なデータをどういうふうに扱うのか。あともそのデータが、暗号化した後、データというものが大きくなるのかという質問に対して、大きくなります。で、確かに、そういう問題を抱えています。ただ、今、彼らの他にも暗号を研究しているところがあって、で、その暗号化された後の暗号化っていうものを圧縮するっていうようなところ、っていうアプローチを研究しているところがあって、彼らもそういうアプローチを研究しているということでした。Yeah, I guess it's pretty good from our side. Do you have any comments on? Can you hear me?
Oh, hi. Sorry, it's cutting in and out. I think there's some network quality issues.
I guess we are quite good with the questions so far.
You're no questions?
Sorry, one more question.
Okay.
Sorry, this is just a quick question. So, will the quantum computer breaks that method? Hello, can you hear me?
Yeah. Sorry.
Will the quantum computer will break that your encryption?
Will quantum? Oh, okay. So yes, addressing quantum computing. So I deal with a lot now with quantum computing threat models with FHE actually, because it's mostly done with post-quantum cryptography and lattices. So yes, to answer your question, quantum computing would break a portion of our cryptographic scheme. I haven't actually done the threat modeling exactly for Umbrel specifically. As far as I know, if I remember correctly, we use the random oracle model in one part. So there is some, I think, some stuff that will be broken. But when it comes to the random oracle model, as far as we know, that's not going to be broken by a quantum computer. So up to that point, it won't be. Exactly what is exposed in Umbrel, I have not actually written that down yet to see what is actually exposed by a quantum computer. But to address the quantum computing threat, I am not at all worried about it. I think it's great that we're having the competition to do the NIST competition, post-quantum cryptography competition, so we can actually find what the best post-quantum algorithms are. But I do not feel threatened at all by it. So to get a little bit more technical about it, data is obviously encrypted with AES 256 or CHA-20 Poly 1305, which is not susceptible, with the security levels we're using, is not susceptible to post-quantum, or not susceptible to quantum computers. As for the elliptic cryptography part, elliptic curve cryptography parts, I am actually quite, what's the word? I don't want to say I don't believe it'll happen, but there's a chance it could happen. For the discrete logarithm problem to be solved, especially with the elliptic curve security that we have, it's going to take quite, not just quantum computer advancements and not just quantum computing research advancements. It's going to take hardware advancements as well. We're talking about fitting more and more quantum gates, logic gates on hardware, as well as error correction. And a part of me wants to think that this is probably not going to happen for at least 50 or more years. There's a lot of people that are saying it will. I just don't believe that. It's the problems that are inherent in these problems are huge. It's going to take a lot more research than just a 70 qubit computer from Google or Amazon or the NSA even. I don't think that's going to happen reasonably soon enough for me to have to worry about it right now. But it is something on my radar, and it is something we've thought about. Lattice-based cryptography offers a lot of protections for quantum computing. But for us to actually change to an algorithm, a proxy encryption algorithm, and design a threshold-based one again in a lattice-based cryptography setting, it's going to take a lot more research and proof of security breaking than that to get me to kind of worry about it. That was a great question, though.
まず質問が、量子コンピューター体制がNuCypherはあるのかっていう質問に対して、いくつかモデルを考えていて、そのいくつかは、破られてしまう。ただ、その乱高と書面っていうんですかね、量子コンピューター体制のある電子書面方式とかを用いたモデルみたいなのを考えていて、そういうものは大丈夫なんじゃないか。で、プラス、量子コンピューターそのものが、すぐに出てくるかっていうと、そうじゃないんじゃないか。そうじゃないっていうことを願いたいみたいな話をしていて、商用化するというか、ちゃんと量子コンピューターというのが実現するまでに、まだまだ数十年ぐらいかかるんじゃないかっていうところで、本当に実用化するまでにちゃんと研究をして、量子コンピューター体制のあるセキュリティっていうものを構築できるように、というふうに思いました。はい。大丈夫そうですね。はい。
みません。データを守りながら活用するということなんですけども、今、本社の中で、データセキュリティすごく大枠的質問なんですけど、今一番良いと思っていると、いろんな方法をご紹介いただいたんですけど、現時点でいいと思っている方法は何か。で、その課題と対策。さっき話出てると思うんですけど、ちょっと。
There's two questions. One is that what is overall, what is the best way to protect your data?
Okay. The best way overall? Well, it's actually kind of a tricky question to answer. So there's something that we have in the security industry that we call threat modeling. So the best way to answer that question would be to begin answering, what am I trying to protect against? And you start there and you start digging into that, and you'll start seeing this is the kind of things that we need to start building for. So for example, you could say, I need to prevent against somebody from just stealing my computer, right? Well, you can start there just by using full disk encryption, and likely that's enough to prevent somebody from stealing the data off your computer from your house. But when we start going out from there and say, just as like a normal person, just the average citizen, right? How can I protect my data online? That's a much larger question. And I think it mostly will just come from being very careful who you give your data to, watch what services you upload your data to, be very concerned about your own privacy. Use strong passwords, definitely always use two-factor authentication, preferably the not SMS-based kind, and always encrypt your data as much as possible. For messaging security, it's like, again, what are you trying to protect against? Because obviously there's different levels of security involved. One is I'm trying to prevent government surveillance. That's one thing that you can say. And there's another one. It's like I'm trying to prevent, someone just from taking my data off my computer, or somebody taking my Google Cloud information or my Apple Cloud information and downloading the data from there. So I would say that the best way is probably one, strong passwords using a password generator, and two, encrypt as much data as you possibly can, possibly and reasonably can. Obviously, it doesn't work well to encrypt every single thing because that then becomes a problem, but encrypt as much as you can and as much as you're willing to sacrifice for encryption.
どういう文脈でデータを守るというか、誰に対してどういう方法をとって、データを共有するのかというところで、どうやってどういうふうなセキュリティが一番いいのかというようなことになりますと。でも、一概に言えるのは、やっぱり強いパスワードっていうものを用いるというところが一点と、できるだけ、暗号化する。できるだけ暗号化する過程を踏む。ただ、それを暗号化しすぎても、面倒くさいし、相手が受け取る側もそれをこうしないといけないので、合理的な数だけ暗号化する。その2点が一般的には言えるんじゃないかということでした。で、そのもう1点が、圧縮方法。
守りながら活用するっていう文脈で、今、御社が一番いいと思っている。いろいろそのデータの内容によって変わってくると、今一番良いと思っている方法に対する課題とその対策、今考えていらっしゃる。
ちょっと、スラックだとかで、ちょっともう一回、フォローアップさせていただきます。
Hi, John. Can you hear me?
Yeah.
All right, so his question is basically about, okay, now we've been talking about how to protect the data, but now when we want to use this data, what is the best way you think it is to use the data while protecting the data? That's basically his question.
Ah, okay. Well, again, it's a very objective answer. It depends on what you want to do with the data and what kind of data it is. There's different ways of using encrypted data, right? So I'll go ahead and give the NuCypher answer to that. So NuCypher is this, essentially proxy encryption is the ability for access control. So what it essentially allows you to do is instead of having to encrypt data over and over and over again and give permanent access to somebody, it's like a key management system for decentralized applications. And so NuCypher will allow you to grant access arbitrarily to any person from a single encrypted piece of data and give them access, and they can use that data. And when they're done, they no longer have access to that data. So if you're to ask me like the best way to, now that the data has been protected, how to actually operate on that data, well, the first answer is, what do you want to do with the data? And then the second one is, well, now that I figured out what I want to do with the data, it's begin figuring out how long I need access, that person needs access to that data, and then limiting the exposure of that data, right? So you don't want to obviously decrypt data and just let it sit on the open internet and allow anybody to take it and use it. You want to encrypt it. You want to give it to somebody for only the time they need it. Once they're done using it, they no longer have access to it. So the best way is from the NuCypher perspective, at least for what we're building and for our applications and our use cases, it is to limit control or limit access to this data to only people and only users who need it at that moment. The moment they stop needing it, they should not have access to it. This prevents leaks. This prevents unnecessary exposure, and ensures that people only have access to it when they need to, nothing more. That way, a great way to say this is in the form of privacy. Privacy is all about consent. It's digital consent. It's literally, I give you permission to do something with something that is very personal of mine, information. I give you permission to use my personal information. And when I say you should no longer have access to that data, then I'm revoking consent. And then you should not have the right and the ability to use that data anymore. And that's what NuCypher is all about. It's the best way to do it then is the ability to grant and give consent as needed. And that's what I think makes NuCypher really powerful, is that ability to digitize consent.
どのようにして、データを守りながら活用していくのかっていうところで、気にすべき点は何なのかっていう質問に対して彼が答えていたのは、もちろんその文脈、何に使うのかっていうところで、方法というか、それぞれ異なるんですけれども、注視すべきところは、まず何に使うかっていうところ、あとどのぐらいの期間、このデータへのアクセスが必要なのかっていうところが、2つ重要なポイントなんじゃないかというふうに言ってました。で、NuCypherがどういうアプローチを取っているかというと、キーマネジメントシステム 的なアプローチを取っていて、まあ、アクセスする権限を誰にあげるか、まあ、その期間はどのぐらいかっていうものをこうコントロールして、まあ、できるだけそのデータの質みたいなところをコントロールする。そういうアプローチをNuCypherは取っているというふうに言っていました。いかがでしょうか、こんな形で。じゃあ、大丈夫そうですかね。はい。So, yeah, yes, we are all good with the questions. So, thank you for the really, really good presentation.
Thank you.
Okay, so can you stay up? We would like to take a group photo
Sure.
with you. Yeah, I like that.
Just let me know when the photo is being taken.
Yeah, right now. Yeah, we are now trying to gather in front of.
Sure.
はい、ぜひぜひ。もし問題なければ。
We are now trying to take a photo right now. Hey, one more. Sorry.
All right.
Thank you so much.
Thank you.
So, 今ですね、まあ彼ら、まあ、春頃取れるかっていうのをちょっと調整中で、もしかしたら取れてたとしたら、まあ彼らが直接また講演できる機会っていうものを作りたいと思いますので、はい、ぜひその時はよろしくお願いします。So, we're now, planning to, whether you can come to Tokyo in person in like spring.
Yeah, that'd be great.
So, yeah, thank you for taking time. Thank you for the great presentation.
Yeah, thank you so much for giving me the opportunity. It was a pleasure.
Yeah.
All right. Take care, everybody.